How do you give a soul to something that doesn't really exist? I mean, how do you take a silent, lifeless drawing and actually teach it to move? Now, this isn't science fiction. This is the fundamental challenge that every single roboticist faces, breathing life into a digital ghost. Take a look at this. It's got a body, it has limbs, it seems to have a purpose. But right now, it's just a 3D model. It's like a statue that's trapped inside a computer. It has absolutely no understanding of its own shape or how its joints are supposed to move, or even that it has joints to begin with. So the question is, how do we bridge that gap? How do we turn this digital ghost into a machine that can think and move? And this, well, this is our map. I know it might look like a really complex web right now, but trust me, it's the exact path we're going to follow to awaken our machine. We're going to keep coming back to this as we uncover each piece of the puzzle. So, our first step on this journey is to write the robot's very soul into a kind of blueprint, a universal language that any machine can understand, telling it everything it needs to know about the body it lives in. That language is called URDF, which stands for the Universal Robot Description Format. The best way to think of it is like the robot's digital DNA. It's really just a simple text file that meticulously, piece by piece, describes every single physical aspect of the robot. This thing is the foundational document for everything, and I mean everything that comes next. And here's the secret. It doesn't matter how complex a robot looks. I mean, whether it has 1,000 parts or just 3. Its entire physical reality boils down to just 2 core concepts: links and joints. That's it. And this is where that theory slams right into reality. Over on the left, you've got the abstract idea. These green blobs are links, and they're connected by the blue cylinders, which are the joints. Now look to the right. You can see it in a real CAD model. Every one of those components, the main body, the wheel, that sensor mount, is a link. And the connections between them? You guessed it, those are the joints. Okay, so a link is basically any rigid part of the robot. But it's way more than just a shape. The URDF defines its visual appearance, what we see, but also a separate, often much simpler shape just for calculating collisions. And it defines physical properties too, like its mass and inertia. Now this is really clever, because it lets a robot look super complex and detailed, while its brain only has to calculate collisions with a simple shape, which is way, way faster. It's all about efficiency. And a joint is what connects 2 links together. It's the rule book for their relationship. It defines exactly how they're allowed to move. A joint can be fixed, which just locks 2 parts together so they don't move at all. It can be revolute, which is kind of like a hinge on a door, or continuous, for something like a wheel that needs to spin forever. Now, you might be thinking that writing this whole URDF blueprint by hand sounds, well, pretty tedious, and you'd be absolutely right. Luckily, roboticists don't start with a blank text file. They start in what I like to call a digital sculptor's studio. They use really powerful 3D computer-aided design software. You've probably heard it called CAD. Tools like Fusion 360, SolidWorks, and CATIA, this is where the robot's physical form is first sculpted from, digital clay into a precise functional model. And while all these tools have different strengths, like Fusion 360 is awesome for quick design and teamwork, while SolidWorks and CATIA are absolute powerhouses for super complex engineering, they all share a common goal: create a perfect 3D version of the robot. And most importantly, they can all export their designs for robotics work. The whole process is actually pretty streamlined. First, you design the robot in your CAD tool. Then, right inside the software, you tell it which parts are links and how they're connected by joints. After that, you use a special plugin that basically acts as a translator. And finally, with just a click, it generates a complete ROS2 package. You can think of that as just a neat little folder that has not only our URDF blueprint, but everything else the robot's brain needs to understand and use it. Okay, our blueprint is complete. The digital DNA has been sequenced, and now for the magic. Now we start the digital awakening, and we bring our creation to life inside a virtual space. So, let's go back to our map. The journey from ghost to machine kicks off right here, with that URDF file we made. This is the source code of the robot's physical existence. But for now, it's just static. It's just a description. The first active player in this process is a little program called the Robot State Publisher. Its one and only job is to read our URDF blueprint, and then it just continuously broadcasts the robot structure, the relationships between all its links and joints, as live data that other programs can listen to. It's kind of like the town crier, shouting out the robot's anatomy for everyone to hear. But a structure is pretty useless without movement, right? So a second program, the Joint State Publisher, comes online. This thing is super handy. It reads the URDF to see which joints can actually move, and then it automatically creates these interactive sliders. So when we move a slider, it publishes the new position for that joint, basically telling the whole system, hey everyone, the elbow is now at 90 degrees. So you have these two streams of information, the robot structure from one publisher and its joint positions from the other, and they both flow into our viewing chamber, a tool called RViz. RViz just listens to all this data, puts it all together, and reconstructs the robot for us in a 3D space. And there it is. The digital ghost is given a body. It's not just a static model anymore. It's a fully articulated, interactive digital twin that we can pose and we can inspect, all born from that simple text blueprint we started with. Success. This journey, going from a drawing in a CAD program to a descriptive URDF file, and then finally to a live visualization, this is the absolute bedrock of modern robotics. It lets developers see and interact with their creations long before a single piece of metal ever gets cut. And the real beauty of this process is just how incredibly versatile it is. It works for these hyper-precise, complex industrial arms like this universal robot, where every single angle and movement has to be perfect. And then the exact same pipeline works for a totally different kind of machine, like this rugged, all-terrain Leo rover, which is designed to go out and tackle the real world. The principles of links, joints, and visualization, they're truly universal. So, we've done it. We've successfully brought a digital ghost to life. We can see it, we can move it around, but it doesn't interact with anything. It doesn't know about gravity or friction, or what happens when it bumps into a wall. So what happens when we take this model and drop it into a world that has rules, a world with gravity? That is our next story. Howdy har. Ha!